Hello students, welcome back to Math 332 Linear Algebra. In this video, we are going to look at the concept called the dimensions of a vector space. All right, so recall that given a vector space, you should be able to find a collection of vectors that can span the space and at the same time, they are linearly independent. And we call that collection of vectors as a basis for that vector space. And we also learned that for a given vector space, the basis need not be unique. So for example, in R3, you can find a standard basis for R3, but you can also find a basis that is different from the standard basis. However, we have a theorem which says that even though basis for a vector space could be different, but the number of vectors for the basis is always going to be the same. All right, so for example, in R3, if you look at the standard basis, you can see clearly that there are 3 vectors in that standard basis for R3. If you find another basis for R3, one thing for sure is that the number of vectors in that basis is also going to be 3. And we're going to call that the number of vectors for a basis, for a vector space, as the dimensions of that vector space. So in this video, you're going to see that there's a lot of questions which basically ask you, what is the dimensions of that vector space? So the way to solve it is very simple. First, you have to identify a basis for that particular vector space, and then you simply count the number of vectors in that basis. And that will give you the information for the dimensions of that vector space. All right, so without further ado, let's get right to this concept. All right, let's begin by looking at the objective for this section. So at the end of this section, you should know the definition of a dimension of the vector space. And more importantly, given a vector space, you should know how to determine the dimensions for that vector space. All right, let's begin by looking at the theorem, one very important theorem that basically gives you the justification for the concept of dimensions. All right, let's work in Rn, and then we will extend these concepts to other vector spaces. But now, let's assume that W is a subspace of Rn. Then the theorem says that any 2 bases for W will have the same number of vectors, okay? So for a vector subspace of Rn, you can find many bases for that subspace W, but the theorem here guarantees that the number of vectors for those bases, they are going to be the same, all right? The number of vectors, they are going to be the same. And that is how we define the dimensions for that vector subspace W. So the vector subspace W, okay, has a dimension. That dimension is the number of vectors in a basis for W. You can write the dimensions of W like this also, okay? All right, so let's look at some example. So we know that the dimension of R3 is 3. How do you know that? Well, you look at a basis for R3, so choose one basis, any basis. So let's choose the easiest one, which is the standard basis. So we all know that this is the standard basis for R3. So let's count. This is one vector, this is the second vector, this is the third vectors. So there are 3 vectors in that basis. So the dimensions of R3 is defined as the number of vectors in the basis. So that is 3. Okay, so let's look at the vector space P2. So the vector space P2, okay, so the vector space P2, as I said, all this theorem stated for Rn, but this Rn can be replaced with any general vector spaces and you still have this result, okay? All right, so P2. So P2 is a polynomial of degree at most 2. Find a basis for that vector space. There are many bases, but we know the easiest basis that you can think of is this. This is a basis. This is in fact the standard basis for P2. So how many vectors in that basis? 1, 2, and 3. So this gives you the dimension of P2 as 3. Now you can extend this result pretty easily to see that the dimension of Rn is n and the dimensions of Pn is n plus 1. Okay? All right. So now the vector space which consists of all the 2x2 matrices. What is one of the bases that you know? Well, the standard basis is the easiest one. So we can write this thing down. This is clearly one of the bases. And in fact, this is the so-called standard basis for this vector space. So again, let's count the number of vectors in this basis. 1, 2, 3, and 4. Right? So the dimensions of this vector space is 4. And you can also see that in general, the dimensions of vector space consists of matrices of size m by n is m times n. Okay, you can use the multiplication rule to see that. Okay, so let's look at the next example. So this one is going to be slightly more complicated. So what we have is that clearly we have a vector subspace of R3. So everything is in R3, but we are not looking at the entire R3. We're actually looking at a plane that passes through the origins. So the question is, hey, what is the dimension of this vector space? So in order to answer these questions, we have no other choice but to first identify a basis for that vector space. So we know how to do that from before. So everything here is basically just kind of like a review of the skills that you obtained from the previous lessons, which is how do you find a set of vectors that span the space, and also how do you verify that they're independent and therefore you have a basis. Right now is you just add one more steps, which is once you have a basis, you just count the number of vectors in the basis, and that will give you the dimensions of that vector space. Okay, so how do we find a basis? Well, what are we looking for? We're looking for all the x and y that satisfy this relationship. Okay, so we're looking for all the x and y that satisfy this relationship. So basically, we are looking for the solutions for these equations. And you know that this is a solutions, this is equations. If you write in the augmented matrix, this is what you get. Right, you can add 0 to it if you want to feel a little bit more comfortable and try to solve for the x, y, z. Right, so this is already a RREF matrix, so we know this is our pivot. So we write x, y, and z. So x is equals to move all this thing across, and we know that this is minus 4z plus 2y. And what are the free variable? The free variable are the y and the z. That's the reason why we have this. So immediately you will see that everything that is in W can be expressed as a linear combination of these two vectors. Everything that is in that vector space W can be expressed as a linear combination of these two vectors. So we get that the span of these two vectors will be the entire vector subspace W. All right, which means that the plane, so geometrically speaking, we are in R3. So this is a Z, this is a X, this is a Y. We have the plane that passes through the origin, and everything on every vectors that is on this plane can be expressed as a linear combination of that two vectors. Once you have this information, you can very easily verify that they are independent. They are linearly independent. You can set up these equations and show that it reduces to this, so your K1 and K2 have no choice but to be 0. So this immediately gives you that this is a basis for that vector space W, and then once you have that, you count the number of vectors. This is a 1 vectors, 2 vectors, so they give you dimension 2. So this is pretty intuitive. You probably have heard of people say that like a plane is 2 dimensions, the entire space is 3 dimensions, and actually you can also show using the same methods that a line that passes through the origins, okay, this is also a vector space, and you can kind of see that this is a vector space which have dimension 1. So dimension 1 objects, dimension 2 object, dimension 3 objects, okay? So it's not counterintuitive. This is actually things that we expect, okay? So let me ask you a quick questions right here. So we are in R4, okay? We are in R4, so we have a vector subspace in R4. So we're looking for all the W, X, Y, and Z that satisfy these two conditions. So this is obviously not the entire R4, okay? Because they have the special requirements that you need to satisfy. So this is a subset of R4. In fact, it is a subspace in R4. So the question is, what is the dimension for this vector subspace? So what you need to do is to find a basis for this and then count the number of vectors in that basis. So the hardest part is to find a basis. If you can find a basis, finding the dimension from the basis is super easy. You just count the number of vectors in that basis. All right, I'm going to give you a moment to think about these problems, and you should pause the video, and when you think you already have the solutions, you can restart the video and we can compare our solution together, okay? All right, let's look at the solution for this problem. So what we're going to do is we're going to find the W, X, Y, and Z that satisfy these two equations. Okay, so let me say it again. You're going to find the W, X, Y, and Z that satisfy these two equations. That is the same as saying that, hey, we want to solve the system of equations. All right, this is the equations obtained by writing W equals to X plus Y and this is the equation that we obtained by writing y equals to x plus z. So you put the system into this augmented matrix and row reduces it to this RREF matrix. So now this is w, x, y, and z. So you write w, x, y, and z. So look at the pivot. So the pivot's w. Okay, the pivot w is obviously equals to minus z plus 2y, and then the x is equals to minus z plus y. So you have two free variable, y is y, z is z. So you can rewrite that equations w, x, y, and z, as you can see now, has the solutions that is spanned by these two vectors, 2, 1, 1, 0, and negative 1, negative 1, 0, 1. So this gives us information on the span of these two vectors is w, and obviously very easily, if you look at these two vectors, use the definition of linearly independent, double check that if you set k1 of these vectors and k2 of this vector and set equal to 0 vectors, your k1, k2 actually has to be 0. That show linear independence. Actually, it's very easy to see that they has to be linearly independent. So now the sets form a basis. So once you have a basis, everything is straightforward. You just have to count the number of vectors in the basis. So how many vectors do we have in the basis? 1 vectors, 2 vectors. So the dimension of that vector space is defined as the number of vectors in that vector space. So that gives you the dimension of W is 2. All right, so as you can see, it's very easy to get the dimensions of the vectors if you know how to find a basis. And from this two example, you can also see that in order to find a basis, usually the first very important thing is to find what span the space. What is spanning the space is critical, because if you don't know what is spanning the space, you don't know how to verify whether those vectors are linearly independent, because you don't have any vectors to verify. Okay, so finding the span will be a very critical steps. Okay, and the different questions will have different way of finding the span, but as we have seen from the videos where we learn how to find the span of a vector space, we basically cover everything that you need to know already. So a question like this should be pretty easy at this level right now. Okay, all right. So now let's switch the concentrations away from Rn. So we no longer in Rn. In fact, now we are in the vector space P2. That's the polynomial of degree at most 2. This is vector space of polynomial of degree at most 2. You have a subspace of it. You can verify this is actually a subspace. We're not doing that, but if you have time and you want to practice a little bit more, you can also verify that W is actually a subspace of P2. So this is not the entire P2. We are actually looking for all the polynomial of degree at most 2 that satisfy these conditions. Okay, P1 has to be 0. Okay, P2 has to be 0. Okay, there are two different ways of solving this problem. I'm going to show you both. So let's look at some of the element that is in this W. So what kind of polynomial that's in this W? Well, obviously 0 polynomial is in this vector space W. And what else? Well, okay, so think about it and find what are the bases for this particular vector space, and then count the number of vectors in that basis. That will give you the dimensions. Okay. All right, I will give you a moment to think about these problems, and you should pause the video, and when you have the answers, you should restart the video and we will look at the solution together, okay? All right, welcome back. So now we are looking for polynomial in P2 such that P1 is 0 and P2 is 0. So select a polynomial that is in P2. It will be of the form of Px equals to a plus bx plus cx squared. We are not looking for all the a, b, and c, because these two conditions, we require P1 to be 0. And P1 to be 0, substitute x equal to 1. You will see that P1 equal to 0 require your coefficient a plus b plus c has to sum up to 0. And P2 0, well, that will require your a plus 2b plus 4c will have to sum up to 0. So you are actually looking for polynomial of this form where their coefficients cannot be any numbers. Their coefficient has to satisfy these two relationships. So we want to solve for a, b, and c. That's the same as putting all this thing into this augmented matrix and row reduce. So that is your REF matrix, and you can see we have two pivots. We have one free variable. So your a is 2c, your b is minus 3c, your c is c. So apparently all the A, B, and C here can be written simply as a multiple of C. So A is 2C, B is minus 3C, and C is C. So you can factor everything out, and you will see that your PX that is in W must be of this form. They cannot be anything but the multiple of this polynomial, 2 minus 3x plus x squared. So the span of this W is this vectors. This is the only vectors that span the vector space W, because every vectors in W is a linear combinations of these vectors. It's a multiple of these vectors, okay? So the entire vector space is basically spanned by only one vectors, and that vectors is 2 minus 3x plus x squared. So this is a non-zero vectors by itself. So obviously this is actually linearly independent. A non-zero vectors by itself is linearly independent. So say for example, v1 is not zero. So if you set k1 v1 and set it equal to 0, you have no choice. The k1 here has to be 0. So by definitions, your v1 is linearly independent. So this is not a zero polynomial by itself. So obviously this is independent. So therefore this form a basis. So the basis for W is simply consists of this vector. So the dimensions for this vector space is going to be 1. All right, so the dimension for this vector space is going to be 1. This is one way to solve it. We are looking for a plus bx plus cx squared such that p1 equal to 0 and p2 equal to 0. This significantly restrict what kind of coefficient for a, b, and c. All right, a, b, and c cannot be anything, but has to satisfy that two set of equations, and that gives you the answers right there. That is another way of solving this problem without using this kind of row reduction and all kind of algebra here. And it is actually also pretty straightforward. So remember, we are looking for a polynomial. Okay, we are looking for a polynomial of degree at most 2 that has p1 equal to 0 and p2 equals to 0. And if I ask you to think about what kind of polynomial have that kind of property, and it also have to be at most degree 2, you realize that if you want to have p1 equal to 0, then you must have this as a factor. All right, so if you try to factor your polynomial p of x, the p of x must have this as one of its factor. And if you need to have p2 equal to 0, so your polynomial also must have this kind of factor. So in fact, polynomial of this form will be in W. Do you agree? Polynomial of this form, obviously you can see that p1 obviously 0, p2 obviously 0. This is not a big surprise, because if you know your algebra from before, knowing a 0, we know that x equal to 1 is a 0 for a polynomial, then x minus 1 is going to be a factor for that polynomial. X equal to 2 is a 0 for that polynomial, so x minus 2 will be a factor. So what are the polynomial that is in W? Well, this is one of them, but this is also one of them, right? This is also one of them. This is also one of them. In fact, we have many, infinitely many, as long as they looks like this. This constant here can be anything. That's the reason why all the px in W will looks like this. And do we have the same answer as this? The answer is yes, because if you multiply out these two factors, so you have x squared minus 3x, right? Okay, x squared minus 3x plus 2. That is x squared minus 3x plus 2. So you can also see from here that everything that is in W is basically spanned by this polynomial. So we get the same answer also. So there are two different ways to solve this problem, but you get the same answers. The basis is basically just consists of these vectors. So the dimensions for this particular vector space right here is 1. Okay, we know that P2 has dimension 3, right? So we know that this is not everything that is in P2. So we know the dimensions has to be less than 3. So our answer is either 0, 1, okay, 2, or 3. This is not 3, so it's either 1 or 2. Not really 0. There's only one way you can get a dimension 0. That is, a vector space consists of only one vector 0. That is when you get dimension 0. So it's not this either. So now the answer is either 1 or 2. And we have seen that actually the answer is 1. Okay? All right. So this is another example involving a vector space that is different from Rn. Now we are also look at another example that the vector space here is different from Rn, and it's not P2, but it's our familiar matrix vectors, the sets that consist of all the vectors which are matrices of size 2 by 2. But okay, now again, so this is obviously W is a subspace of this vector space, and this vector space here is dimension 4. Okay, so this one is not everything that is in. This is a special matrix. We are looking at all the matrix that's symmetric. All right, so this is definitely not all matrices of size 2 by 2. So this here, the answers here, the dimension have to be less than 4. So it could be 0, 1, 2, or 3. Obviously not zeros. Same reason. This only vector space that has dimension 0 is a vector space that consists of only 0 vectors. So that's not the case. So this is either, so the answer for this will be either just 1, 2, or 3. Okay, so which one is it? Well, so you have to try to figure out how it's if you have an element that is in this set, how is that element looks like? What is a symmetric matrix? So symmetric matrix is something that's like this. This is 1, 2, 4, 4. This is a symmetric matrix, right, of size 2 by 2. If you transpose this, now look at how I interchange the row. I write as my column. I write this row as my column. Okay, I'm actually doing that row. I write as column. This second row, I write it as second column. And after you have done it, you see that they are basically still the same. They are the same. So this is what we call a symmetric matrix. So symmetric matrices has this property. After you interchange the row and column, you get the same matrix. So these are called symmetric matrices. Right. So what is the dimensions of a set which consists of all the symmetric matrices of size 2 by 2? How do we do that? Well, we have to find a basis. Okay. So how do we find a basis? Well, we have to find something that spans this space. All right. So look at the property for symmetric matrices. You'll realize that if you have a matrix A that looks like this, let's say you have 1 and you have a 5, and let's say you have a 3 and you have a 2 here, then immediately this matrix is not symmetric, because if you transpose it, okay, you have 1, 3, and then you have 2, 5, and you'll see that they are different. And the key thing, that the reason why they are different is that these two numbers here are different. If these two numbers here is the same, then you will get symmetric matrices. And also, another observation is that these two numbers here need not be the same. Things that's on the diagonal can actually take different value. The key thing is the things that's off diagonal must be the same. So in order to make a symmetric matrix, the symmetric matrices must look like this. Okay, 2 by 2 symmetric matrices must look like this. If you have an A here, you can have a different B here. But if you have a C here, you must have a C here. So everything that is in this set that has to be symmetric must be of this form. So let me rewrite this. Let's say I write my A here, so you can see that this is how I can rewrite everything. My B here can be like this, okay? And then in order to get the off diagonal CC, I will have to do this, okay? I will have to do this. All right, so what do we have right now? Well, basically we have that everything that is in this vector space, which means that every matrix that is symmetric, must be written as a linear combinations of this matrix, and this matrix. So we can verify, I mean, in fact, I just told you how, that every symmetric matrices must be spanned by this vector here, and this vector here, and this vector here. So once you have the span, it's very easy to verify that these three vectors, they are actually linearly independent. So this form a basis. So this is actually a basis for that vector space W, which consists of all the 2 by 2 matrices that is symmetric. So because of that, let's count the number of vectors in the basis, 1, 2, and 3. So, well, that gives you the dimension of that vector space. W is 3. So, all right, that concludes our discussions on the concept of dimensions of a vector space. In the next video, we are going to look at a new concept called change of basis. So recall that for given vectors in a vector space, you can write the coordinates of that vectors relative to a basis. So let's say that particular vector space has 2 different bases, and for the same vectors, we can write the coordinate for that vectors relative to the basis number 1, and we can also write the coordinate for that vectors relative to basis number 2. The question is, how is that 2 coordinates related to each other? Okay, so for that particular particular questions will be answered in the next video. Okay, I will see you then.